Okay. Uh, Hello everyone. Today I will be sharing about the Raft consensus algorithm. And so let's first talk about what is a consensus algorithm. The problem we're facing here is high workload. Like if in Shopee, in some promotion day like 5.5 or Double 11, there is much higher QPS we need to handle. So uh, so there's two ways to handle this. The first way is what we call a vertical scaling. Vertical means that we handle those extra high loads by buying better machines, like expensive machines, more better CPU and more memory. The the cons of the vertical scaling method is that it's expensive. Like after some threshold, the machine can get really expensive and not economic. And the second thing that is limited performance. Like there's a limited of how performant, how good a machine can be. So perhaps it's not enough to handle all the workload we have. The second solution is horizontal scaling. That is, we buy a lot of machines, but normal cheap computers. So with so many computers, we can connect them together and form a system, and we can get linear scalable performance, which means the more machine we add into our system, the higher the performance is. So that's what we call linear because it's ON. Yeah. And for the second method, horizontal scaling, how we normally design it is using the master worker model. So basically, we have in a system of thousands of computers, we have one master node, which store the state of the application and control everything. The other type is the worker that actually do the work. So for example, in Google File system, we have a master node. Every client, if you want to read a file from GFS, you connect to master. A master will have all a map of if you want to read this file, well, this file is stored in some other worker nodes. So the master will direct the client to those worker nodes to actually get the file. A master will also handle the update, deletion, rename of all the files, but they only store the metadata. So yeah, in the GFS though, the actual file is stored in the worker node. You can have a lot of worker node. So they actually store the file chunk and they talk to the client to send or receive the files. Another example is Kubernetes. So in Kubernetes, we have a control plane, which is the master node. The master node will handle all the client requests. For example, if you want to update the version of the app you are running, you talk to the master, say, well, I want to kill those containers. I want to create new containers running the newest version. So the client only talk to the master. The master will handle all the creation, updation, delete of the containers in the worker node. So the worker node will actually run the containers. So the problem we have here in the master worker model is that we have a single point of failure. That is, if our master died, the whole system died. So that is a very serious problem. So in order to make our system more reliable, we can have a solution that is, we can have multiple masters. Like we can replicate the masters into 5, 7 or more more nodes. So if one of the master node crash, it doesn't matter because we have other replications. And one of the other replications will be the new master. So even if one master dies, we can continue to work. We have a new problem now. with the multiple replica solution. That is, we need to decide who, if the old master die, who will be the new master. So if we don't handle this properly, perhaps when the old master die, there are two other nodes who both think that they are the new master. So they both start to handle client requests, and different clients have different requests. So they both start to manipulate the worker node, and the worker node see this master want me to do this, and the other master want me to do this. So it will crash or just don't work properly. So that is what we call a split ring problem. We need to avoid this. Another thing is we need to persist the data. Like the old master, as it is running, it have a state in memory. When we get the new master, we have to make sure that the new master have exactly the same state as the old master, because you can't just, because a master node died, the whole state change and the worker node doesn't know what to do next. So we need to have the same data as the old master, the same metadata as the old master. So that is what consensus algorithm about. This is the solution. So it's about provide a fault tolerance. Like fault tolerance means we can have a earthquake that destroy the whole city, and but as long as we have other master replica running in another city, we can still work. Yeah. The fault tolerant, by allowing our system to continue to work as long as some of the servers are available. Like for example, if we have 5 replicas of the master node, as long as some of them are living, we should be able to continue working. So for here, the sum of the server, we might need to try to define it. So normally when we talk about things like Paxos or Raft consensus algorithm, normally we need the majority of the servers to be alive. Like if I have 5 replica, I need at least 3 of them to be alive. If only 1 of 5 servers are alive, it doesn't work either. So, but however, there is other type of consensus algorithm, or yeah, that will work as long as there's at least 1 server available. For example, the chain replication, you can have 5 replicas, but as long as 1 of them is working, the chain replication will work. But this is not what we talk about today. What we talk about today is Raft. So we can assume that we need the majority of replica to be working. So before I talk about Raft, I will talk about Paxos first, because it's really interesting. So the Paxos before Raft is created in 2013. Paxos is basically the only consensus algorithm. And it is famous because first, it's the only one, and second, it's really hard to understand. There was another algorithm called view stem replication, but I never read about it, and I don't think it's ever used in practice. So we just focus on Paxos here. Paxos is created by Leslie Lamport in 1990. So he also created the text and the Lamport timestamp. Lamport timestamp is another thing used in distributed system. It's a logical clock. Yeah. The first paper about Paxos is the part-time parliament. It's written in 1990 by Leslie Lamport. And in this paper, he actually write a story. Like he literally write a story about a parliament trying to determine the law in the land, in the island of Paxos. He chose the island of Paxos because while he is creating this algorithm, he is having a vacation in the island of Paxos. So the whole paper is a story. He thinks that by explaining Paxos in the story, it will help other people to understand Paxos. But it didn't work. So nobody actually understand, almost nobody understand this paper in 1990. There's only one person that understand. So this paper only get published 8 years later. And I think he has really get tired of people telling him that Paxos is so difficult to understand. So he write a new paper in 2021, called Paxos Make Simple. So the abstract of the new paper is the Paxos algorithm, while presented in plain English, is very simple. So, but it's still not. If you actually try to read the paper, it's not that simple. So let's talk about Raft. Raft is created basically just because Paxos is too difficult to understand. It's created by a PhD student and in Stanford. So they actually do an experiment. They teach two different classes. One teaches a student about Paxos, another one teaches a student about Raft to make sure that Raft is easier to understand. So to achieve this understandability, Raft divide the consensus algorithm into two sections. That is leader election. This part solve like if the old master died, who will be the new master? So it's the leader election. Another part is log replication. This part solve the problem of how do we make sure that the new master, the new leader, have exactly the same state as the old leader. So one thing that Raft doesn't solve is Byzantine fault. So a Byzantine fault is like, what if one of our node doesn't run normally or is hacked or something? So we assume that all nodes according to the rule is act normally. So we don't handle the Byzantine fault in Raft. So let's first talk about how does the leader election work. We need to introduce some terms, something first. So first thing is role. So a node can have one of three roles. So it can be a leader, which is a master I used to talk about. So we will call them leader now. So leader will be the one who handle the client request. Every client, if you want to talk to the system, you talk to the leader. It will also be responsible to replicate the data to followers. And you also need to send heartbeat RPC to followers to remain the leader. So if you want to keep being a leader, you need to send heartbeat RPC to followers. Followers, they need to receive data and actually replicate them. So that's why we talk about replica. Candidate is those nodes that ask a vote from others. They are trying to be the new leader. So we have three roles here: leader, follower, and candidate. Another thing is term. You can think about a term is the increasing number that every node will remember which term it is in. In every term, there is only at most one leader. For example, Obama is the president of the last term, and Trump is the president for in this term. So it's basically the same thing. In Raft, we have a term, and is increasing, and there's only at most one leader in each term. Let's talk about leader. So leader, as I said, you need to send heartbeat RPC, because if you don't people will just assume that you are dead. So if you want to tell people you are alive, you need to send up a heartbeat. The other thing is, as a leader, you need to handle the request from client, and you need to replicate state to the followers. For candidate, you need to ask other people to vote for you, so you can be a leader. Once you receive the vote from the majority of the nodes, so it's pretty democracy. If we have 5 nodes and you receive vote from 3 of them, well, you are the leader now. And there's some detail called candidate timeout. We will explain it later. So basically, if you are still a candidate after a long time, you will just assume this term just doesn't work. Like in a election, like if 2 people, perhaps they both have the same vote and they wait and wait, they never have the majority of vote, well, they just assume this term is stuck. So they are stuck. They just increase the term and try to be the leader of the new term. Okay, I think okay, the follower will have the election timeout. Basically, as a follower, I will be expecting to hearing from leader. If leader doesn't talk to me for too long, I will assume the leader is dead. So I just try to be a candidate and try to be the new leader. So that is the let's look at what might actually happen in a election. So let's assume we have a system of 3 nodes, S1, S2, and S3. In the beginning, everybody is a follower, and everybody have a term of 0, and nobody is a leader. And everybody have a random election timeout. So S1 have 150, S2 160, S3 300. So nothing happened, and until 150. So this is when the S1 election timeout get triggered. So you will see that, well, I didn't receive any message from leader. I assume that the leader is dead, so I will just be the candidate. So it will first increase the term from 0 to 1, and you will become a candidate, and you will vote for itself. Yeah. And then you need to ask other people to vote for it. So it will send the request vote RPC to S2 and S3. So let's assume that the RPC take really long time, and at 960, at 160 milliseconds, S2 actually get the election timeout triggered. So the same, it will assume that the old leader is dead. It will increase the term by 1, with the term 1, and it will vote for itself. It will be a candidate. It will send the request vote RPC to S1 and S3. Let's assume that actually S2 and S3 is in the same place. So the RPC is a lot faster. So S3 actually received the RPC from S2 first. So S3 will check, well, my term is 0 and the S2's term is 1. Okay, I will vote for you. So S3 will vote for S2. And S2 received the RPC from S1. So S2 will also check, well, my term is 1, your term is 1. We are both the candidate. I will not vote for you. So it doesn't vote for S1. So here we can see that S3 actually remember that it already voted for S2 in turn 1. And 10 milliseconds later, S3 received the RPC from S1, which we sent here. So after S3 received it, since it already voted through S2, it doesn't vote anymore. So it just say, well, I won't vote for you. And 10 milliseconds later, S2 received the response from S3. So S2 can see, okay, I have a vote from myself, and I have a vote from S3. So now I have 2 votes. 2 is the majority of 3. I am the new leader now. And S1 will see that both S2 and S3 refuse to vote for it. So it just still only have 1 vote. So currently the situation is that S2 know that it is leader now, and S1 still think that it's a candidate, and S3 think that it's the follower. And then S2, since it become a leader, it will start to send heartbeat RPC. So it send heartbeat RPC to S1 and S3. S1 will see that, okay, you are the new leader, I will become the follower again. And so does S3. So that is how we do the election in the basic form. So that is how we get from nobody is the leader to have 1 leader. There are some questions can be asked, like, what if everybody become a candidate at exactly the same time? Nobody will ever have a majority vote. Well, that is the case here. In the beginning, everybody is a follower, and everybody have a timeout of 150. So they will all become the candidate in 150. They will all vote for themselves. And as you can see, they will all send request vote to other people. And the other people will all respond with no. So what will happen is that everybody, after a long time, everyone is still candidate and still only have one vote from themselves. That is what does the candidate timeout used for. So it's also a random number generated. For example, in this case, S1 actually, it started to be a candidate here. So 100 milliseconds later, it did a check. I'm still the candidate. So I will increase the term. So the term is now increased from 1 to 2, and you will vote for yourself. And you will have a new candidate timeout generated. It will do the same thing, just request vote from S2 and S3, and S2 and S3 will check, well, you have a larger term than us. Okay, so you are the boss. We will vote for you. And later S1 will receive 2 votes, and you will get all 3 votes. And it's a leader now. So that is how we solve the problem if like everyone, if we don't have a majority, actually we just wait for someone else to increase their term and start from the beginning again until we have a majority vote and then new leader will be generated. A new question is what if there is a network partition? Like if we have 5 nodes and 3 of them in city 1 and 2 of them in city 2, if the network doesn't work between those 2 cities, what will happen is that only partition A will be able to elect a new leader. The nodes in partition B just simply don't work. Yeah. So only the partition with the majority will get to work. If there are 5 partition and no partition is have the majority, just everybody die. There's some more edge case, so it's okay if you don't. The edge case is that what if we have a symmetric network partition? Like what if A and C can talk, C and B can talk, but A and B can talk and cannot talk. So if either A or B become leader, the other one will just assume the leader is dead and start a new election. So the problem is basically A is a new leader, and after some time, B think A is dead. So B start a new election. And since B can vote for itself and can get vote from C, it will become the new leader. And then same story again, A will think B is dead. So the same. The solution, we have a list or pre-vote. So basically, the follower will make sure that, for example, for 100 milliseconds, if the old leader have talked to me within the previous 100 milliseconds, I will not vote for the new candidate. So that's what we call the pre-vote. So C, as long as you can talk to A, you will never vote for B. So that's solve the problem. The takeaway here is that in each term, there is at most one leader. There can be 0 leader in some situation. And this leader can communicate with the majority of the nodes, since it needs to talk to the majority of the nodes in order to be a leader. That is the first problem we have, leader in action. The second problem we have is persist state. Like, how do we make sure that the new leader have exactly the same state as the old leader? So the first thing we do is the state machine. We, instead of actually store the whole state of the application, we store the log. That is mean if we have we need to create something like Redis, instead of store the state, we store the log that lead to this state. For example, we have a log of 3 commands, and each command will contain the term that is created in. So the first command set x to 0 to 1. The second command set x to 2. The third command set y to 1. So finally what we got is x is 2 and y is 1. So we actually only store log. We never store the state. The second thing is that we hide log by default. Like, for example, if the client talk to us, they insert this log, we will actually hide it from the application, from the database, until we have replicated this log in the majority of the nodes. So we only show the committed log to the application when we replicate the log to the majority. So I will tell you the reason behind it later. So first, let's look at how does the leader do the replication. So when you receive the new command, you actually need to replicate this new command to all the followers. So let's say we have a leader of 8 log, and we have a follower, it only have 5 log. How do we make sure that the replica the last 3 logs to the follower? We will send RPC. So in the first RPC, we will ask the follower, do you have a log at index 8 with term 3? The follower will say no. So we will continuously move forward, like from 8, it doesn't match. From 7, it doesn't match. From 6, it doesn't match until when the cursor get to 5, it match. So this is when the follower say, okay, I match. I will replica. Everything follow this. So this is the simplest situation, but this is basically everything about replicate. So I will stop here. The thing I want to talk about is majority. So why do we hide a command before it's replicated to the majority? Why do we only show the commands to the application after it's replicated to the majority? Because there's one thing about majority that is two majority always overlap. Let's, for example, in this 5 nodes, the majority is 3. So if 1, 2, 3 is a majority, you select any 3 other. If you try to create another majority, you have to select at least 3 nodes. And if you select 3 nodes, you have to at least select one of 1, 2, 3. So let's say this is majority A. If you want to create a majority B, you can get 4, you can get 5. and then you have to select one of 1, 2, 3. So two majority must overlap with each other. So this is the thing, the rule. So how do we make sure the new leader have exactly the same log of the old leader? So that is during the election. Like remember when we talk about leader election, we say that the follower just check for the term and vote for the first candidate that ask it to vote. Well, that is not the whole story. It actually do another check. That is, it only vote for the candidate if the candidate's log is at least updated as my log. Like example, if S3 received the request from S2, S2 want S3 to vote for itself. So S3 will actually check through, let me see your logs. If your log is as updated as mine, well, I will vote for you. But if your log is like too stale, you don't have any log that I have, well, I won't vote for you. So that is how, that is just a rule. So this rule will achieve our goal. For example, if we replicate a new command in 1, 2, 3, and then in the next election, 1, 2, 3, if 4 asks 2 to vote for itself, 2 will see that 4 doesn't have the new log, so 2 won't vote for 4. So 1, 2, 3 will only vote for within this group, and they will never vote for 4 or 5. Let's do a proof here. So why does the new leader always have exactly the same state of the old leader? Or to put it more concisely, the new leader will always have all the committed logs. Committed, I mean, if the log is replicated in the majority, we will commit it, we will show it to the application. So the proof of why does the new leader always have all the committed log is this. So let's assume a log L1 is committed. If it's committed, it means that it's replicated to the majority of nodes. Let's say that the majority of nodes that have L1 is M1. And in order to be a new leader, you need to receive votes from the majority of the nodes. So let's call the majority of nodes that vote for the new leader M2. So we have a log L1, and M1 is all the nodes that replicated L1. M2 is all the nodes that vote for the new leader. Since the majority rule, there must be at least one node A, such that A belongs to M1 and also A belongs to M2, because M1 and M2 are both majority. So two majority must overlap. Let's assume they only overlap at node A, or at least let's say node A is one of the nodes that is overlap between M1 and M2. So since A belong to M1, so A have L1, because M1 is all the nodes that have L1. So A belong to M1, so A have L1. And also, since we only vote for the leader if the leader's log is at least as updated to us. So since node A voted for the new leader, so the new leader's log is as updated as A. So the new leader must have L1. I think that's all. So that is why we say the new leader must have all the committed logs of the old leader. There might be cases where the new leader don't have the some uncommitted logs, but that will be okay. This is the core of Raft. So we solve one problem of leader election, and then we solve another problem of data persist. That's all. the next step is, let's get into the practice, the implementation, like how now I know about Raft, how do I write it? So it's actually really easy. So there is one cheat sheet you can find in the paper. It's basically pseudocode. So it defines all the RPC arguments and results, and how should you handle the RPC. It's basically a really detailed design. So if you want, you can take a look at it. And if you want some more production level implementations, you can check out the EPCD. It's written in Golang and TiKV. It also have a Raft implementation in Rust. Both of this implementation are pretty standalone, so you don't actually need to know about EPCD or TiKV to read them. Another optimization is that, remember we say that we only store log, but if we only store log, there is possibility if we run for a long time, the log are too many logs. So for some time, we periodically we might take a snapshot and delete all the logs before. So if we have 1,000 logs, perhaps we can delete the first 901 and just take a snapshot and only return the rest log. So we don't need to store everything that had ever happened. This is called log compaction. Another thing is faster match. So remember when we talk about the replication, we need to move the cursor one by one. So there's a situation where the follower is like really stale. Like, what if the leader have 1,000 log missed in the follower? So we can do faster match. So I won't talk in detail because it doesn't really matter, but you can read the paper. So the paper just doesn't really talk about it that much. You have like one paragraph. It's actually easy, so I will just skip this. And if you want to write the application on top of Raft, it's really straightforward. You just need to handle the log and read the log and apply them and get your state. And Raft will handle everything else for you. So we talked about Paxos before. I will give a brief introduction of Paxos. The Paxos algorithm described in the paper that we talked about, the Parliament paper, it actually only select one value. Like only select, okay, everybody agree, we agree on one. That is it. That's everything that Paxos do. Only select one value. So in practice, we need to implement something multi-Paxos. It's not clear what exactly is multi-Paxos. It basically is anything that you read the Paxos paper and you implement a system, and you can call it Paxos. You can call yourself multi-Paxos. So because the writing is also very vague about how to implement multi-Paxos. Actually, Raft can be seen as one of the implementation of multi-Paxos. They have a lot of variation, but in general, it looks very similar. For example, in Paxos, in multi-Paxos, we also use log to represent the state. We also rely on the majority to resolve the conflict. We also only commit the log when the log is replicated to the majority. And in Paxos, there is also a concept of term. So Paxos is the round number plus the server ID. The difference is that in Paxos, when we compare multi-Paxos with Raft, any node in Paxos can be a leader. So it doesn't have, it don't have the check. So the leader will actually learn from the followers about the absent committee logs if we have some absence. And Paxos support out of order commit. For example, we talk about the log. In Raft, it have to be applied from 0 to to above 1, 2, 3, you can't skip anything. But in Paxos, you can do out of order commit. Another thing we talk about is chain replication. We see that this thing can work as long as there's one server remains. So what is chain replication? That you just chain multiple servers together, and all the write requests need to be handled by the head. All the read requests need to be handled by tail. So yeah, I think it's quite straightforward to why does it work. So let's say if something in the middle crash, you just have it connect to the next one, and you just, okay, I write, for example, if you need write to x21, head will store that and tell the next will store x21, and tell the next will tell x21 and tell the tail. So tail will, when we read from tail, if the command have been passed to tail, you will get the newest value. So it's really simple, and it's used in some simple system like elastic block storage. The good thing about it is that it's just really simple. So but the bad thing is that you still need a coordinator. Like, what if this one and this one, they have a partition, and you need a coordinator to tell that there's something wrong and relink the chain. Another thing that the throughput is limited by the slowest node. If one node is like out of memory and really slow, the whole process will be stuck there. Another comparison we can make is with peer-to-peer consistency, like Bitcoin. We also talk about replicate the logs in Bitcoin, replicate the block in Bitcoin, but across multiple nodes, of course, in Bitcoin, the nodes count is a lot larger than Raft. There is something similar between Bitcoin and Raft. One is that they both have a proposer. Like in Raft, we choose who can propose the new log by using the election, leader election. And in Bitcoin peer-to-peer, we use the hash calculation, like whoever first calculation the the right hash will get to create a new block. So that's similar with, we all have a proposal. And that it's also similar in how do they handle the conflict. If there's a conflict, the majority win. Like if three nodes, say in index 10, we have this command, and other two nodes say we have other command. Well, only the majority will be able to elect the leader, and the leader will resolve the conflict by deleting anything that is conflict with itself. So if there's a confliction in Raft, it will just resolve them by using the majority. And in Bitcoin, at least, it's actually the basic same. So in peer-to-peer system, we decide the win by compare the length of the logs. So it leads to the fact that the majority, like if everybody see this is a longer logs, well, they will join this. So if you are the longer one, everybody will join you. So you will, in the end, you will be the majority. So similarly, peer-to-peer also using the majority win strategy to solve the conflict, but it's more like less straightforward because it's using the length comparison. Okay, that is all of my sharing.
All right, thank you, Wang Hao. So thank you for the amazing lecture about Raft consensus. So we have a couple of questions from the audience. So Chen Chen has a question of how to keep track of the total live nodes at the moment.
Yeah, that's the one thing I missed out is that in the basic Raft, you need to set the group in the beginning. Like when you create your Raft system, you need to say, I have 5 nodes here and their IP address is this, and let's talk to each other. If you want to change the membership, if you want to delete a node or if you want to add more node, you need to, there's another thing called membership change is in the paper, but I never read it, so I didn't share it. But yeah, it's possible.
Okay. We have another question from Kenrick. So this means that everyone would send an RPC to everyone else, right?
Yeah. Not everyone. Leader will send RPC to everyone else.
During the election phase.
Yes.
Okay. Then Ricky has another question for when there's a case that there are 2 candidates requesting for election, then each voter needs to determine who to vote for. So that's what's happening, right? So when the voter needs to determine who to vote for, how does he decide? Because there are 2 candidates.
Okay, you vote for the first candidate that whose log is as updated as you. Like if 2 candidates both want to be the leader, and let's assume that they both have the newest log, so you just vote for the first one.
Okay.
The first you receive the RPC from, yeah.
Okay. Then we have a follow-up question from Chen Chen. So this means that potentially Raft is not easy to extend in real time.
No. The membership change is already written and approved in the paper. Yeah, so you can change you can add node, you can delete node in the runtime. Yeah, it just I don't know. So I don't know how to. So I didn't read it. So yeah, but it's possible. It's okay. Yeah.
Okay. We have another question from Huizing. So it's talking about the case where election occurs. So if the minority is discarded, what is the implication in the real world scenario where the state change is initiated by a client? Does the client receive an error message that their transaction failed, or?
Yeah. So basically, you can just tell the client, like if you find the log corresponding to the client request is somehow deleted, you just tell the client it's deleted, and the client just retry.
Okay. I think that is all the questions that we have. And I think some of us are looking forward to Professor Wang Hao's part 2.
Thanks.
All right, so thank you for the presentation.
Thank you.
I think that's all for today that we have for Aki. Yeah, so I'll see you guys next week.
Okay, see you everybody.